Okay, should I start or?
No, just let me share this. Let me share link with the participants so that they can join as well.
Okay, okay. You tell me.
Yeah. So let's start. Welcome everyone to the live session of 2-week refresher course in computer science on next generation technologies sponsored by Ministry of Education. We have our keynote speaker, Andreas Kassler. Andreas Kassler is currently full professor of computer science at Kassler University, Sweden, which he joined in 2005. From 2003 to 2004, Dr. Andreas Kassler was assistant professor at the School of Computer Engineering, Nanyang Technological University, Singapore. He is co-chairing the Distributed System and Communication Group and maintains an active research program in the fields of networking and cloud computing, with main research focus on wireless meshed networks, software-defined networking, future internet, data center networking, and quality of service. He is co-authored of around 130 peer-reviewed conference and journal publications, 6 European or international patents. He served as a guest editor of a featured topic in Eurosip Wireless Communications and Networking Journal, and served as associate editor on the editorial boards of some referred international journals. He served as a technical program committee member for many international conferences, chaired the TPC of International Conference on Advances in Mesh Networks and international workshops on wireless mesh networks. Dr. Andreas Kassler is a senior member of IEEE Computer Society and IEEE Communications. He is also management committee member of several cost actions. On this note, I request Professor Kassler to take over, and I request the participant to post their questions in the YouTube chat box. We will take them in the end. Over to you, Professor Kassler.
Thank you, Vipin. My pleasure to be here today and talk about how we can accelerate virtual network functions to improve the flexibility and the performance. This work is based not only on my contribution, but also several other of my postdoc and PhDs like Jonathan Langle, Deval Bamare, Jonathan Westin, and so on. So as you all know, current networks like the internet, as we see here depicted, they adapt its resources and they flexibly adapt the sending rate to have a best effort delivery mechanism. And a prominent example of such protocol that utilize that is TCP, which adjusts the sending rate depending on the available capacity. BGP is the routing protocol used in the internet, and we have 50 years of experience in deploying and managing that network. And the internet has been designed to be very simple. The more complex operation on the end hosts, and that was part of its success story. But at the end, people started to realize several functions are missing and deployed middle boxes to augment its functionality. And at the end, the internet now is a very complex and ossified beast. And the flexibility is very much limited in terms of if you would like to introduce new functionalities. It's very difficult to innovate, to provide new use cases. So if you would like to introduce new protocols, and if the switches should process different headers, that requires hardware upgrades, that requires lengthy standardization processes, and that is super difficult to do. And we need to convince manufacturers to make new ASICs and create new switch generations or router generations. And then they need to buy new hardware, they need to put them into operation, and that's very costly and is very inefficient. So on the other hand, we see new use cases that are currently popping up that require flexibility from the networking fabric and predictable performance. So we have autonomous driving that is becoming very hot in the next 10 years, autonomous manufacturing, which basically requires deterministic networking support to provide you low and predictable latency and jitter. We have remote surgery coming, we have immersive gaming, autonomous drones, smart grid integration of the energy grid with real-time control. We have new use cases that require even more bandwidth and lower latency. And so the current take is that the network needs to become both more flexible, but more predictable in their performance. So how should we do that? And if you take a step back and think about how the networks are designed and managed, then we see that the routing protocol in the internet, they typically depend on manual configuration. They have a very local view. They try to find a single path between a source and destination address, and they have relatively coarse fault recovery. So if something happens with some configuration, they require several seconds to converge to alternative path, and they shift traffic in a pretty much uncontrollable way upon failure. So there have been several accidents, like here in this example, Australia's internet was cut off because Malaysia ISP has a route leak because of misconfigured BGP protocols and so on. So you see that in addition, we also have new use cases like data centers that recently pop up and are very important for hosting our services, which require automation in order to manage and configure a large number of switches and routers, and require very fast reaction to failures. And you would like to make very fine-grained routing decision on a per tenant basis, and you have many, many 100,000 of tenants in a database, so you need very fine-grained routing and forwarding decisions, and you would like to have not a distributed control, but a centralized control. So in order to serve these kind of use cases of the data centers and improve the way that routing can be done to avoid this manual configuration, there has been recently a very important trend that we call software-defined networking. So what is software-defined networking? In a traditional router in the internet, as you see here in this example, we have a closed box, which is composed of the data plane, which is a very high-speed networking fabric to forward packets from the ingress to the egress port at terabit speed. We have a control plane, which is basically run on a generic operating system in such a switch. And then we have different applications that, for example, run services for routing, traffic engineering, load balancing, and so on. And these boxes communicate and exchange information to form a distributed control plane. So in order to centralize logically the control plane, basically what the software-defined networking principle advocates is we should break up these boxes and we outsource out of these boxes. We make them very simple, and we put a network operating system that we call the SDN controller on top, which is logically centralized, making logical centralized forwarding decisions, and the application we put on top. Maybe this application can talk with something called the SDN controller talks with this now very simple switches using a standardized southband API, how we call it. And then basically what we do is we move the control plane out of these devices and make these devices programmable from control plane perspective using applications, right? And then we can dynamically upgrade the functionality by deploying these applications on top of this network operating system, which is something like running on a Linux server and is interacting with northbound API. And this northbound API, we can use maybe Netcore, or we can use JSON, we can use web services, and we can even control, therefore, the way how such network is operated and managed, maybe from a tablet, right? Because with a tablet, we can deploy this app that talks JSON to this network operating system. And then through this app, we can install distributed forwarding state in these switches based on our new routing protocol that we would like to implement. So we outsource the brain, centralize this brain, and make this brain programmable. So this is the general of our army, basically, which makes these centralized decisions. based on collected information from our distributed switches that are now very, very simple. So basically how that works in more detail, here we have our new switch. This new switch is very simple. It has a very simple control plane interface only based on this open flow control channel, which allow the SDN controller to install flow table entries into the switch using the southbound interface. Then in this data plane, we have a bunch of tables that govern the forwarding based on this installed states from the SDN controller. And on top, we have our northbound interface and the control applications on top. So the main contribution of this SDN was the standardized open flow protocol, which allows to install flow table entries, query statistics from the switch, and standardize this data plane model as a kind of match action abstraction. So basically, we can install entries into this flow table, tables in these different flow tables that match upon different header fields. And if a match is triggered, you can assign different action that should be executed. And the other contribution of SDN is this concept of a logically centralized control via such a single entity, via this SDN controller to make the control plane programmable. However, new data plane protocol evolution, like introducing new header fields that you would like to match upon, requires changes to the standard. And that means that over time, instead of having 12 OpenFlow match fields at the very first version of the standard, that has been extended to many more match fields. Maybe you can match on MPLS labels, you can match on other header fields, but that requires updates to the standard, that requires update to the switch ASIC here to parse these messages, to provide the support for these matches and so on. And also a very limited interoperability between different vendors that talk, maybe some vendor talks OpenFlow, some vendor talks netconf for southbound interface. But that maybe we can solve with the SDN controller. But the challenge is the limited programmability of the data plane. So if you want to change how your data plane operates, that's not possible really with SDN, because SDN just allows you to install certain flow table entries. And in order to make that more programmable and flexible, we have seen recently some very important trend that I call the rise of the cloud and commodity packet processing. So in 2012, basically, telco vendors identified that, well, maybe we should use an Intel box for packet processing and put all the packet processing functionality in software on cloud data centers and apply principles from cloud on scalability, scale in and scale out, to basically scale such packet processing in software. So that led to this virtualized network function, the VNF approach, to deploy packet processing on x86 servers, which is now very flexible because you can totally change how you process your packets because everything is in software. And basically, you allow the cloud to scale in and out, to scale with the traffic demands. And you can deploy now new packet processing functions within minutes instead of within weeks to deploy new hardware. So instead of having physical router, physical firewalls, physical NAT or DPI box, we virtualize them, put them maybe inside a VM, inside a Docker container. So to create a virtualized router, a virtualized DPI box, a virtualized home location register as part maybe of a 4G network, and deploy them on our common off-the-shelf compute infrastructure that we have in our data center. And that reduce the time to market, we can automate the whole process, we can orchestrate it, we can connect the different packet processing microservices together to form a service mesh, and we can leverage, if we deploy everything in containers, we can leverage basically microservice architecture for fine-grained scalability. So this second trend that I think is very important is this network function virtualization, where the network functions are software pieces run inside containers or virtual machines. And we use SDN to connect these different containers together to form what we call network slices. We deploy them on our data center on our NFV infrastructure, we have an orchestration platform that tells us which container to place where, how these containers should interact with each other. And then they configure the forwarding between these containers using SDN-enabled network, using SDN controllers out of the box like Open Daylight or ONOS. And then you deploy your services in this container platform like Kubernetes. And then basically your services are just a piece of software. And then you can implement maybe a BNG, a broadband network gateway, or a UPF, a 5G UPF, a user plane function inside a Docker container, connected with a firewall, with a video optimizer, and build flexible service chains that scale in and scale out according to the Kubernetes scalability mechanisms. So maybe using the horizontal pod autoscaler, if more users join, it would create new replicas and would load balance across these new replicas, right? So that is the other extreme. Instead of using hardware-based packet processing, now everything moved towards software-based packet processing, right? And we were also active in that area. We have many contributions in that area. I'm not going to mention those, but how about this flexibility, which is given by the programmability by SDN and NFV, would solve all networking problems? Is that really true? But if you think about in more details, where would you like to place these virtual network functions? On the edge data center, on the cloud data center, where do you have the resources to place them? How do they interact with each other to provide you a low latency service experience? How to route the traffic in your networking fabric, over which path to send the traffic of two VNFs that exchange information? How to manage load changes, when to scale up, when to detect that your Docker container runs out of resources. So if you get a burst arrival of packets, maybe that is not possible to scale fast enough. How to predict load changes, you can use machine learning maybe approaches, and how to be flexible and have dedicated performance at the same time. So this is what we're going to talk in the remaining half hour a little bit, how we can achieve this trade-off between flexibility and performance, right? Because we have on one hand side, we have the fixed switches and routers by dedicated hardware that are not really flexible, but they provide you dedicated performance because it's hardware. On the other hand, you have the flexibility of packet-based processing in software, in containers, and you have the flexibility. You can implement everything in user plane and do any kind of things you would like there. But what kind of performance do I get? Where are these NFV performance bottlenecks? And I give you some example. So assume you have a 24-core server, and we have virtual network functions deployed on this 24-core server. And basically how these virtual network functions are deployed, you allocate basically a virtual machine, you pin this to a certain core of a server, and then you have something called a virtual switch in our server, which basically wires this virtual machine with the physical interfaces of the server, and that's a vSwitch here. And for example, in this example, we use 6 cores of our 24-core server for the vSwitch processing, which shuffles the packets between the network interface card, packet driver, and the virtual network function which run in the virtual machine. And basically the virtual machine-based packet processing can be already some bottleneck because of the software implementation. It may run into a lot of cache misses that may lead to latency increase and so on. And also this virtual switch can be a bottleneck because it's software implementation, and many virtual machines need to exchange packet among each other, and they do that through this virtual switch. So the virtual switch may be also a bottleneck. And then in addition, you have the NFV infrastructure that, depending how you configure and how you allocate the resources, what the capabilities are, may be a bottleneck. And the physical switch, basically, that is the attachment point of this server. That's typically designed to run at packets at line rate. That's typically not the bottleneck. So if we take this example here, we have packets coming from the switch to the NIC, and they are passed to the vSwitch, and then they forward to a virtual machine. And then based on this allocation, we use 6 cores for vSwitch, and we use 18 cores for packet processing of our virtual network functions. And then based on that example, assuming 18 virtual network functions, 1 core per VM, each one can process maybe 1 million packets per second. vSwitch, 6 cores, 1 million packets per core, maybe, for example. So basically in this example, the vSwitch would be our bottleneck, because only 33% of our virtual machines can be utilized, right? Okay, so how about a different resource allocation? How about we allocate more resources to the vSwitch, 50% of the cores to the vSwitch, 50% of the cores to the VNFs. Well, and then maybe we have not a bottleneck anymore, but we need 50% of the cores just to shuffle packets from the NIC to the virtual machine and back. And basically that burns a lot of CO2. That requires a lot of capital investment, because our servers are 50% not used for processing of the important packets, right? 50% are just for shuffling of the packets. And there's also the PCIe bus bottleneck. Each packet needs to traverse PCIe bus twice in this example, and you get a lot of jitter due to maybe cross-NUMA actions, CPU sleep modes, TLB misses, and so on. But there's a paper on SIGCOMM 2018 that I suggest to guys maybe to read if you're interested in this kind of research, which shows what's the latency just of the PCIe bus transfer, which depends on the hardware architecture of our server. So you see some hardware architecture provide you a dedicated low and dedicated jitter, while others have much more latency variation, and that may lead to a lot of packet loss, maybe if you would like to have low latency services. So main reason is the x86 has not been designed for general packet processing, and Intel is trying to improve and make it better, but is not really designed for that, right? So, and that basically is, people are realizing that at telcos, saying, okay, how can we now think about our packet processing pipeline that we have to run for our services, and how can we deploy these packet processing engines? How can we break those down into the individual components, disaggregate our packet processing into small components, and deploy them flexibly and on our cloud and edge networks in order to have a very tight integration of our compute infrastructure where our VNFs run and our network, right? So the main idea is now to chop down the whole processing part, chop that down in flexible components, and hardware accelerate them, right? Because hardware acceleration is needed to keep up with the ever-increasing processing requirements of our packets, right? So we need to also provide dedicated performance for our URLLC flows, for our ultra reliable and low latency flows for the brain surgery, and we need to reduce the energy consumption. So if you look at what happened over the years, as I showed you, due to this NFV-based software processing on our commodity servers, we were using more and more CPU cycles just for shuffling the packets between the network card and the virtual network functions that are inside the VMs. So the available CPU cycles for the revenue-generating application reduce over time. The more and more packets you let process by this software-based packet processing approach. So the output per server, due to the VM processing cycles, the available output that is needed for the I/O and the networking thus reduces, right? So, and also due to the slowdown of Moore's law, the cost per packet process also then increase. And that's not something we want to do. So instead of taking a step back and think how we can use hardware now to more flexibly accelerate parts of our packet processing pipeline. And if you look at the trade-offs in flexibility and programmability, on the most flexible side, you let everything process in software, maybe in containers on virtual machine. more closer to hardware is user space processing, maybe using Intel DPDK. Then you can process also packets in the kernel. You can process packets in the driver, or you could improve x86 with specific hardware accelerated features for maybe load balancing. You can augment x86 with an FPGA coprocessor and run your packet processing on the FPGA, or you can basically process the packets on a NIC or in an ASIC to move it out of the x86, right? So the more down we go to the hardware, the more performance we get, but the less flexibility we have in terms of adding new features. So if I make a NIC, ASIC design for my hardware packet processing, that gives me the highest performance. But if I want to change something, maybe I need to reprogram the ASIC. So the question is, how big is this difference in terms of performance that we can get? And I will give you some numbers later on. And what is the benefit of this flexibility? So basically, if I put that in another picture, in another diagram here, on the hardware side and in the software side, and using basically software side packet processing results in very slow performance. Hardware side results in very fast performance. And what's the flexibility? Then basically the x86 is super slow, not super slow, but it's slow, but it gives me the most flexible operation. And the ASIC basically is the most fastest, but the most inflexible one, right? And your choice of architecture impacts this trade-off that you want to do. But where do we want to be? Basically, we would like to be at this sweet spot where we have fast and dedicated performance and the flexibility. So how can we achieve this at the same time? How can we achieve the performance of the hardware at the same time being programmable and flexible? And recently, if you think about the different domains, the slowdown of the Moore's law inspired different people for having specific coprocessors to basically improve the performance. So for example, on graphics, we have a specific compiler that compiles OpenCL to our GPU. On signal processing, we have specific compiler that compiles MATLAB code to a DSP. For the machine learning, we have a compiler that compiles TensorFlow maybe to TPU hardware. And on networking, what language and what compiler should we use and what kind of hardware should we use to basically flexibly compile software on hardware in a reconfigurable way, right? And then basically there has been this seminal paper on reconfigurable match action table architecture, or this PISA architecture, which is basically a very flexible, reprogrammable switching ASIC. And they have been designing a programming language P4, which compiles from very high level P4 language to our switching ASIC functionality. And you can reprogram your packet processing pipeline dynamically without replacing your hardware. So that's the most benefit of this kind of things. So instead of, to motivate this a bit more, instead of current networks that have been designed bottom up, so basically the vendors, they have bought a switching ASIC, which has a fixed function, you cannot change it. And then basically, when you start your building, you define your requirement and the features you want. And then based on that, you select your switching ASIC, your switching platform, and then you have your switch operating system. And then basically, then you try to map your requirements to that. And the network systems have been designed bottom up. But once you decide on a chip that defines how your system will be built, defines how the driver is written, defines how the control plane running with the switch is able to interact with the forwarding plane. Now, of course, if you want to add a new feature, for example, support a new protocol, you need to change the fixed function chipset, which could take 4 years because you need to convince manufacturer that's a good thing to put into this new ASIC generation. You need to update your driver switcher as to make use of these features. And now basically what P4 and this whole programmable data plane movement are trying to do is to design the physiology in a different way, right? Basically what the P4 world tries to do basically what we want to be able is to define exactly at high level how the chip should process our packets. And then we would like to specify that in a high-level language that even master students can implement. And then we would like to have this language compiled to our programmable target, which runs then this packet processing in hardware. And if I need new features, I update my P4 program, I recompile, I redeploy on the same chip, and I would have new features dynamically added, right? And then can we do that? That would be super nice to have. And the answer is yes, we can do that. So there have been several hardware designs that support this reconfigurable match action table principle based on ASIC design. For example, Intel FlexPipe, Cavium XPliant, and Barefoot Tofino, which has also been bought by Intel. On the SmartNIC side, as you see here, there has been also several SmartNIC vendors which have support for P4, which compiles a P4 code to run on the SmartNIC and process packets on the SmartNIC, like from Pensando, from Metronome. You can also compile P4 to normal CPU, to Intel code. There's support from P4 compiler to DPDK, compiler to eBPF, to VPP, vector packet processing, or Open vSwitch, also support for P4. And then also P4 to FPGA programming. For example, there's a NetFPGA platform from Xilinx that you then can compile P4 code and build devices that let us tell them how to process the packets, right? So how would that work in more detail? So we have basically our SDN controller, and this SDN controller would still be used to populate table and now stateful memory cells in our switch. And we would have a control plane on our switch device. And then our switch device would be a programmable data plane device, which supports stateful memory operation and arithmetic operations. So packet come in, they are sent to a programmable parser into individual headers, which is the path representation of our packet. And the programmer declares the headers that should be extracted and their order in the packet. So headers and intermediate results then can be used for further matching and actions. Headers can be modified, added, or removed to our packet. And then basically the programmer defines how the tables and how our stateful processing would look like, and exact processing algorithm. And finally, the packet is deparsed and serialized, and the programmer declares how the output packet will look on the wire, right? And then based on this programming functionality, so plugging everything together, we would have our target platform, maybe our Tofino switching ASIC, our SmartNIC, and the vendor supplies a P4 compiler for that platform. So there's P4 compiler for Tofino, P4 compiler for Metronome, and so on. We have our architecture model that tells us which part of our platform are programmable and how they are connected. Then the user implements a P4 program. And then basically this P4 program is fed to the P4 compiler. The compiler creates a target-specific binary. The binary is deployed, which has empty tables and external objects that are populatable from the control plane using P4 runtime to add or remove table entries, interact with the control information in our data plane with our stateful memory cells, or send packets to the CPU port from our switching ASIC to our control plane. So what are P4 parsers? That's the first step in our P4 pipeline. Basically, a P4 parser is a function that maps packets into headers and metadata written in a state machine style. So every parser has 3 states. It has a start state, it has an accept state where it accepts a packet, and it has a reject state where it says, no, this packet we don't accept. And other states need to be defined by the programmer, say a state called parse IPv4 or a state parse TCP header, and so on. And in each state, you can execute 0 or more statements, and you transition to another state. So then, in addition to the P4 parser, we have P4 control, which are similar to C function, but they do not support loops because of the real-time requirements of such switching ASIC. And we need to give upper bound at compile time on packet processing performance. So that's why we don't allow loops. And P4 controls, we can declare variables, we can create tables, we can instantiate externs. And basically the functionality is specified by code in our apply statement of our P4 control. And basically that represents all kind of processing that are expressible as directional acyclic graphs. For example, match action pipeline, deparser, and updating checksums, and so on. And the interface with other blocks are specified by the architecture types, typically in the forms of headers and metadata. Then we have tables. I give you an example in a few slides how such P4 code would look like to define a table. They are the fundamental unit of our match action pipeline. And compared to SDN enabled switch, which has a rather strict functionality, what kind of actions you can do, you can specify any kind of action that you want to do if you have a match. So basically, in a table, you specify what data to match on. And what is this kind? Is it an exact match? Is it a prefix match? And a list of possible actions. Maybe drop packet or encapsulate into another header that you then implement yourself. And then you can specify also how large this table should be, what's the size, maybe 64,000 entries, what's the default action if you do not have a match, what static entries you want to pre-populate it, and so on. An entry contains in a table key to match on in our packet. That can be, for example, header or metadata, and the action that is executed when a packet match, and potentially a parameter to this action data that can be supplied by the runtime, by the control plane. So I give an example here. This is, let's walk through some steps involved in performing match action processing. So a table consists of a bunch of entries that specify a key, an action ID, and action data. These entries can be added and removed by the control plane. And a table will also specify a default action to perform if no match is found. The table will extract the specified bits from the input headers and metadata to form the key and attempt to find a match with the entries that the control plane populates. If there is a hit, then the action ID and data are read out of the entry. If there is not a hit, then the default action and data are used. And these two outputs are passed into a multiplexer which selects one of the two based on if a hit was found or not. And this action ID and data are passed to the action execution unit along with the input headers and the metadata, which then outputs the headers and the metadata and the result of the action code. And as part of that, it can update headers, it can update metadata fields, it can write something in stateful memory and so on. Right? So let's make an example how to apply tables in controls. So here in this example, this is part of a P4 code. The control is the myIngress part, which basically receives headers and metadata and standard metadata and can modify headers and metadata. So we define a counter of 64 entries, and we would like to count the packets. The counter is called C. We have an action that is called tally, and basically this action would increase the counter corresponding to the ingress port of the packet. Then we define a table called monitor, which matches on the IP4 source address using an LPM match. And it can have two actions. One is it can call the tally action that we specified here, or it maybe not have any action. And then basically this is how we apply this table in this ingress block. We say if header IP version 4 is valid, then we say just table, like monitor table, like table name dot apply. So this is how we apply the table. And then basically if you populate the table from the control plane that is called myingress.monitor with this kind of match actions. We put a IP version 4 source address LPM prefix match 10011. The action name to call would be myingress.tally. We have no parameters. So if you populate the monitor table from the control plane with that match on the packets coming from 10011 and let it count, we would like to do like this, right? So then we would have here for each ingress port, we would count how many packets we received from the IP version 4 source address 10011. Right? So this is very simple code, and that shows you how to apply tables in controls. Then the last step is to do the P4 deparsing. We assemble basically the headers back into a well-formed packet. That's expressed as a control function. There's no need for another construct here because the packet out extern is defined in core P4 program code and basically makes the deparsing explicit. I give you here some more information on packet out extern and so on. But we are not going into more detail. If you want to know more about the P4, we created an online course, which is a MOOC open for everybody to participate. Basically the course runs typically from January to June. It's just finished. So we will run a new instance next year. You can check out. There's your exercises. We provide a Mininet and a P4 compiler to compile to Mininet, and there's a lot of material for you in the course. You can learn how to use it for load balancing. You can use it how to make stateful forwarding, to do tunneling, and so on. But in the rest of my 10 minutes, I want to show you how we can use it to accelerate now virtual network functions with the P4 code, because the P4 enables flexibility. We program bonds and we compile it to multiple targets. So we can compile P4 code to DPDK using this tapas compiler. We can compile P4 to SmartNIC using this metronome compiler. And we compile P4 to Programmable ASIC using maybe the Intel Tofino compiler, right? And here you see the example of a SmartNIC, which has a P4 programmable pipeline inside the SmartNIC itself. So packets then basically can be programmed to be served by the SmartNIC itself, or we can program the packets processing in P4 and deploy them on our tapas container inside maybe a container in DPDK. That gives our way towards what we call intelligent network edge function, because the SmartNIC now enables flexible packet processing. It would accelerate edge compute and speed up distributed application, because packets entering the SmartNIC can be purely processed by the P4 pipeline in the SmartNIC itself, or you can forward specific packets to the virtual switch and process them, or you can forward them towards a virtual machine and process them there. So you can now very flexibly say, should I hardware accelerate my packets, process them in the Tofino, process them in the SmartNIC, or process them in the DPDK, programming just once in P4 and compiling it to different targets. And then you can deploy also different functions, implement bridging, routing, NAT, key value cache, machine learning tasks. We did also in the P4, or now 5G UPF, the user plane function that we implemented in P4 and deployed on the SmartNIC. And I will show you some performance numbers, what you can achieve with a SmartNIC acceleration. So what we can do with the P4, basically we can decouple functionality from the location. We write once in P4 and we deploy the P4 code maybe on the SmartNIC, maybe in the server, on the DPDK or on the Tofino. And in the remaining part, I show you how you can use it to accelerate user plane functions, right? And then the more closer to the user you deploy them, the less latency you have for the packet processing, obviously. And then you can dynamically allocate the P4 code to the different places in your data center, and that results in very flexible deployment. So an example now is the evolved packet gateway, or the UPF, as we say, offloading in the 5G. So the softwareization of the 5G packet core basically, and the SDN allows a user control plane split approach where basically packet gateway you can collapse into the UPF function, as we call it. Basically, this processes user IP packets. Basically, this calculating GTP tunneling processing, VXLAN processing, firewalling. And if you do all these processes on x86, the per packet latency is in the order of hundreds microseconds to 1 millisecond, depending on the load. And the UPF packet processing pipeline looks basically like this. You have a programmable parser. It first goes to layer 2 tables. You check IP version 4, check if the GTP tunnel is there. If you don't have a GTP tunnel, then basically you go for the downlink processing. It goes to the firewall table. You do the GTP encapsulation and the forwarding towards your radio access network. If the GTP tunnel is there, then there's an uplink packet. It goes to the firewall table. You do the GTP decapsulation. You do the IP4 forwarding towards the data center gateway. And basically, here's some more information of the different UPF for the uplink and downlink processing steps. I'm not going into more detail. And we have implemented a hybrid deployment. Basically, we have implemented the UPF MP4, compiled it to Tofino switching ASIC. We have implemented the UPF MP4, deployed them on the SmartNIC, and we have implemented them MP4 and compiled them on the DPDK. And then depending on where you process, you get different latency and throughput characteristics, right? So basically, I give you some performance numbers. Assuming all processing is done on the host only in DPDK. So we compile the P4 UPF pipeline to DPDK, process all packets on the host. Then, as you see, if we increase here the packets per second, this is 2 million packets per second. So this is our achievable latency. So the latency basically increase after, let's say, 1.2 million packets per second, and we will have packet loss because of our saturation of our CPU. And this is the different performance number depending on how many GTP tunnels we have. So the highest latency we have for around 100,000 GTP tunnels, and the highest jitter we have. So the jitter and latency is in order of 100 microseconds here per packet for 128 byte packets. And the table size has big impact on DPDK because of cache miss, branch misprediction, and long latency instructions. If we instead compile the P4 UPF and let everything processed by the SmartNIC, so basically that will be the following performance. So here you see already we can significantly increase the packet per second. So this 5 million packet per second, and the latency is still below 20 microseconds, right? And then basically you can support around 5.5 million packets per second by processing on the SmartNIC, and the table sizes have not much impact on our performance. So 3 times throughput compared to host processing we can achieve. And SmartNIC has 60 micro engine that process packets at around 800 megahertz, and the host has 3.2 gigahertz. So one lesson also that we learned is if your packet processing pipeline is super complex and you need many operations, the SmartNIC will not give you good performance because the CPUs that are used inside the NIC, if it's not an ASIC, it's just much slower than if you do the processing at the Intel, but you save PCI transfer 2 times the PCI, right? And then the other is now we can also do a hybrid deployment where parts of the processing we do in SmartNIC, parts we do in DPDK. And here I showed you the latency of packets that are processed in the tapas, processed in the DPDK, and processed in the SmartNIC. And you see here different latency numbers here. So if we increase the load and put more and more packets towards the SmartNIC, also the latency increase. And here is basically showing you the latency of the packets that are processed in the DPDK, and here the latency of the packets that are processed in the metronome. Basically, that is also showing you the packet latency CDF for 3 million packets per second, 10,000 GTP tunnels. And this is basically this experiment here, where we have 3 million packets per second and 1.5 we have processed in SmartNIC. That's a SmartNIC latency curve, and 1.5 we have forwarded to DPDK and processed in DPDK, and that's a DPDK latency. And also our colleagues from Ericsson and our friends from Ericsson and Campinas, they deployed the UPF on Tofino, and basically the latency of Tofino is very predictable because it's compiled to ASIC, and then you see the latency is between 1 and 2 microseconds, just depending on the packet size, irrespective of how much line rate you have. So I give you some pointers to some of our recent P4 work that we also were looking into. We implemented like load balancing at layer 3 at the network layer. We did some network telemetry event-based system. We did some cyber physical event detection for real-time networking. We had some machine learning pipeline inside the SmartNIC. We can use also SmartNIC for security accelerations for certificates and so on. Right? I think I'm at the end of my talk. So recap a little bit from the network. So on this axis, we show you the configurability of the network, or the flexibility of the network. Here we have static networks. Here we have programmable networks, fully programmable network. On the other axis here, showing you a little bit of performance or determinism. So on the left-hand side, we have best effort. On the right-hand side, we have much more predictable performance. Clearly, we would like to have the most flexible and deterministic network fabric. Internet, as I showed you, is quite inflexible. It's best effort. Industrial networks provide you a lot of determinisms, but are also not really programmable. They're more configurable, and enablers is like TSN. Data center networks, on the other hand, are much more programmable with the SDN, but do not really provide you determinism. And SDN and NFV are enablers. I would argue 5G is much more providing you determinism and relies on data center networks for deployment. And then in order to increase determinism, people are working on DetNet and on TSN. The question is how we can increase the flexibility. And I hope I convinced you today that P4 is a very good point to making networks much more programmable, flexible, and by flexible deployment and hardware acceleration, we can also increase determinism. And this opens up the way towards P4-based programmable, fully programmable 5G, TSN, and deterministic networking. So networking 2021 is softwareized, virtualized, hardware accelerated. We have new challenges from digitization, vertical industry, dynamically changing functionality. I try to make the point in this talk to make networks more flexible, more deterministic, more performant, and I hopefully raised more questions to you. And then that's the end of my talk. I would like to say thank you, and I'm here to answer questions that you may have.
Thank you, Andreas, and thank you for sharing such a brief introduction of P4 and how this can be used with UPF and other 5G components. So thanks. And we have some questions on like if you can differentiate like how service chains is differentiating from network slicing. So is it same, or what do you think about it?
Well, network slicing, basically you can implement with the service chains easily, but the main important point is the resource separation. So you would like to allocate certain resources to network slices. And then you need to make that very much clear how you allocate and deploy them and so on. But service chains is one method to deploy network slices.
And one more question is on what do you think about futures of this VNFs if you compare them with the CNFs, cloud native network functions? So what do you think, or can we do some kind of can we use P4 in this CNFs like as a whole pipeline as a part of it?
I think that's a very good point, Vipin, and I think we are getting slowly towards that direction. There is some still limitation that you cannot do in the P4 world, which makes it like difficult to have it as a generic tool for VNF. Say, for example, crypto acceleration, that depends pretty much on the target. If your hardware platform support that as an external function or not. So that's not specified in the standard, but can be used as external function. The more important limitation, I would say, is the queuing management and buffering. So that's also not programmable. And having maybe fine-grained resource allocation on a per-user basis maybe is required for use cases such as UPF or BNG. And if you use Intel Tofino, you cannot allocate 100,000 different queues. So that's very difficult, and you cannot program them. You can just configure, like the traffic manager in the P4 world is just configurable. But we are working on a project with Red Hat on how to use XDP and BPF for making packet scheduling, maybe packet queuing, scheduling, programmable also on a normal Intel server, accelerate that with the XDP and make it programmable maybe through to P4, and then maybe that's also very interesting towards the next generation.
That's true. Completely agree. And we have one question on can you tell more about your course, like what you do on, like, it's like what is the structure? Is it 3 months course or something? What you teach in Kassler University on P4?
So the course is basically 3 different modules. The first one is, so each module is 1.5 ECTS, and it runs basically 6 weeks, each module. Module 1 is on introduction to P4. So you get all the language constructs and you get familiar with the Mininet programming environment of P4. You install the virtual machine to give you the programming environment, and you get few exercises. You will implement encapsulation mechanism. You will implement some very simple P4 functionality, table match actions, and so on. Course number 2, or the module number 2, is on load balancing. So we will look into congestion-aware load balancing, how that works in a data center, ECMP, non-congestion-aware, non-stateful versus stateful load balancing. And finally, we will look how we can implement that with P4. And then using Hula, or you look into Conga, and we make congestion-aware forwarding decisions on the switching fabric. And the last part is more on like industrial, making stateful forwarding configurable, from the making more stateful forward register actions, and these kind of more advanced constructs, and also looking into advanced data structure like sketches, Bloom filters, how we can implement them in P4.
Yeah, although we have, thank you for sharing this, and although we have more questions, but let's take them offline, and participants can ask these questions on discussion forum as well. And then we can take these questions offline as well. So on behalf of the organizing team, Open Technology Foundation, Frost and Teaching Learning Center, Ramanujan College, University of Delhi, we extend our heartfelt thanks to you, Professor Andreas, for taking out time and interacting with our participants. We really hope to have more engagements with you in the near future. Thank you so much.